Good day everyone, I'm Joanna Marie Balbin, a graduate school student from NUST, and today we will discuss polymer nanotechnology. Let's start with defining what polymer is. A polymer is any class of natural or synthetic substances composed of very large molecules called macromolecules that are multiples of simpler chemical units called monomers. Polymers make up many of the materials in living organisms, including, for example, proteins, cellulose, and nucleic acids. Moreover, they constitute the basis of such minerals as diamond, quartz, and feldspar, and such man-made materials as concrete, glass, paper, plastics, and rubber. Look at this picture. This is a chemical structure of polyvinyl chloride or PVC. Industrial polymers are synthesized from simple compounds joined together to form long chains. For example, polyvinyl chloride is an industrial homopolymer synthesized from 15 units of vinyl chloride. The word polymer designates an unspecified number of monomer units. When the number of monomers is very large, the compound is sometimes called high polymer. Polymers are not restricted to monomers of the same chemical composition or molecular weight and structure. Some natural polymers are composed of one kind of monomer. Most natural and synthetic polymers, however, are made up of two or more different types of monomers, and such monomers are known as copolymers. Polymers play a crucial role in living things, providing basic structural materials and participating in vital life processes. Example, the solid parts of all plants are made up of polymers. These include cellulose, lignin, and various resins. Cellulose is a polysaccharide, a polymer that is composed of sugar molecules. Lignin consists of a complicated three-dimensional network of polymers. Wood resins are polymers of a simple hydrocarbon isoprene. Another familiar isoprene polymer is rubber. Look at this example. This is a natural rubber latex stuff from a rubber tree in Malaysia. Other important natural polymers include the proteins, which are polymers of amino acids, and the nucleic acids, which are polymers of nucleotides, complex molecules composed of nitrogen-containing bases, sugars, and phosphoric acid. The nucleic acid carry genetic information in the cell. Starches, important sources of food energy derived from plants, are natural polymers composed of glucose. Inorganic polymers also are found in nature, including diamond and graphite. Both are composed of carbon. In diamond, carbon atoms are linked in a three-dimensional network that gives the material its hardness. In graphite, used as a lubricant and in pencil leads, the carbon atoms link in planes that can slide across one another. Synthetic polymers are produced in different types of reactions. Many simple hydrocarbons such as ethylene and propylene can be transformed into polymers by adding one monomer after another to the growing chain. Polyethylene, composed of repeating ethylene monomers, is an addition polymer. It may have as many as 10,000 monomers joined in long coiled chain. Polyethylene is crystalline, translucent, and thermoplastic. It softens when it is heated. It is used for coatings, packaging, molded parts, and the manufacture of bottles and containers. On the other hand, polypropylene is also crystalline and thermoplastic, but it is harder than polyethylene. Its molecules may consist of from 50,000 to 200,000 monomers. This compound is used in the textile industry and to make molded objects. Who coined the term nanotechnology? The term was coined in 1974 by Norio Taniguchi of Tokyo Science University to describe semiconductor processes such as thin film deposition that deal with control on the order of nanometers. His definition still stands as the basic statement today. Nanotechnology mainly consists of the processing of separation, consolidation, and deformation of materials by one atom or one molecule. Why is nanotechnology important? Nanotechnology improves existing industrial processes, materials, and applications by scaling them down to the nanoscale in order to ultimately fully exploit the unique quantum and surface phenomena that matter exhibits at the nanoscale. This trend is driven by companies' ongoing quest to improve existing products by creating smaller components and better performance materials, all at a lower cost. A prime example of an industry where nanoscale manufacturing technologies are employed on a large scale and throughout is the semiconductor industry, where device structures have reached the single nanometer scale. Your smartphone, your smartwatch, tablets are all containing billions of transistors on a computer chip the size of a fingernail. Some senses, nanoscience and nanotechnologies are not new. Chemists have been making polymers, which are large molecules made up of nanoscale subunits, for many decades, and nanotechnologies have been used to create the tiny picture on computer chips for the past 20 years. However, advances in the tools that now allow atoms and molecules to be examined and probed with great precision have enabled the expansion and development of nanoscience and nanotechnologies. Let us now proceed to polymer nanocomposites. Polymer nanocomposites consist of a polymer or copolymer having nanoparticles dispersed in the polymer matrix. Polymer Nanotechnology Group will develop enabling techniques for the patterning of functional surfaces. To better understand what polymers are, let us have this video.
Almost 50 years ago, a scientist named Richard Feynman predicted the future of nanotechnology. He predicted what needed to be done and how it might be done, all before anyone had really even seen an atom with a microscope. It was 1959, only 2 years after the first satellite was launched into space, and it would be another 2 years before the first manned spaceflight.
Why can't we write the entire 24 volumes of the Encyclopedia Britannica on the head of a pin?
Feynman, one of the most brilliant people of his time, asked that simple question. His talk, "There's Plenty of Room at the Bottom," would become a roadmap for nanotechnology. Feynman looked into the future and predicted how technology might make things smaller and smaller. How small? The size of atoms.
I don't know how to do this on a small scale in a practical way, but I do know that computing machines are very large. Fill rooms. Why can't we make them very small? Make them of little wires, little elements. And by little, I mean little. For instance, the wires should be 10 or 100 atoms in diameter.
Today, the smallest parts inside a computer chip are about 100 nanometers. What's a nanometer? 1/1000th of a meter. That means if you laid 1 million of these computer parts side by side, they would measure only 1 inch across. Few years, these parts will be only a few atoms. Computers will be hundreds of times faster.
But I am not afraid to consider the final question as to whether, ultimately, in the great future, we can arrange the atoms the way we want. Very atoms all the way down. What would happen if we could arrange the atoms one by one the way we want them?
In 1989, Don Eigler and his colleagues at IBM did just that. They moved individual atoms, 35 in all, to spell out IBM. 40 years after Feynman predicted the future. Today, scientists are using nanotechnology and making things smaller and smaller.
In their ongoing quest to improve existing products by creating smaller components and better performance materials, all at a lower cost, the number of companies that will manufacture nano products by this definition will go very fast soon, and soon make up the majority of all companies across many industries. Evolutionary nanotechnology should therefore be viewed as a process that gradually will affect most companies and industries all over the world. I hope you learned something from this video. Thank you for watching. God bless and keep safe.